All right, very good morning to all of you. I'll begin today's session. So previous class we were discussing MOSFET, power MOSFETs. Now power MOSFETs had a vertically oriented structure, and when you look from the top to the bottom, the structure will have metal first, oxide layer next, followed by the semiconductor layer. And the device operates based on the principle of field effect. Therefore, we call that device as field effect transistor, of course, and then metal oxide semiconductor came from top to bottom when we looked at the structure. Therefore, we name it as MOSFET, metal oxide semiconductor field effect transistor. And then we discuss the operating principle. The channel that is formed is called as the inversion layer, because when you look into the structure, there will be the p-type body layer and the N plus source interface. Now that interface, there has to be a channel that must be created. That channel was created by applying the gate source voltage, by applying the field effect. So because the channel is created in the p-type body layer, that too an N channel or a channel made of free electrons, that is created in the p-type layer. Electrons are minority carriers in the p-type layer. Therefore, that layer is called as inversion layer. So drain current flows from the drain through the inversion layer or through the channel, and then it flows to the source terminal. That's what we discussed in the previous session. Today's session, we will discuss the VI characteristics. That is very similar to a BJT, that will be very similar to a BJT. And then we will discuss the switching characteristics, which is again quite simple because the switching will involve only the capacitances, various capacitances that are stray capacitances, of course, that are going to be featuring during the operation. So on that note, I'll start sharing my screen. Right. So today's session will be on the VI characteristics, VI, and of course the switching characteristics of MOSFET. VI characteristic is under steady state condition, whereas switching is going to be the transient characteristics. So you can understand them to be the transient and the steady state characteristics of power MOSFET. Transient refers to switching, steady state the normal VI characteristics. This is what we will be discussing today, 24th February. Fine. Now, before I begin, I must write down the name of that layer. The layer through which the drain current flows, that is called as inversion layer. Please remember this key term. Of course, this comes under operating principle or previous session, inversion layer. This will be formed between the p-type body layer and the N plus source layer. Or we named this as channel, N channel, source layers. We named this as N channel. This is what we did in the previous session. But inversion layer is a better term and important term as well. So we try to remember that. We'll be discussing steady state VI characteristics. Beyond that, I didn't tell any technical point. All right. So now steady state VI characteristics is a plot of the power terminal parameters, which is ID versus VDS, drain to source voltage, right? So this is what steady state VI characteristics is all about. It's exactly similar to a BJT, power BJT, but there will be one difference. Of course, in power BJT, there was quasi-saturation and hard saturation, and there was the active region and cutoff region as well. Whereas here we won't have those two regions. We will have ohmic region, we will have cutoff region. We will see what are they. ID versus VDS. For various values of course, that is understandable, source voltages, because gate is the control terminal and MOSFET is a voltage controlled majority carrier device. Therefore, for various values of VGS, we need to plot ID versus VDS. Now the plot is going to be like this. Now, so this region, beyond this region, the device will get broken, or this portion. This is breakdown region. We don't operate it. We don't operate the MOSFET over there. This is the maximum drain source voltage, VDS. You can name it as VDS max, VDS yes, anything. So beyond that, we don't operate. Not operated. Not preferred. Run away. That is the perfect term. That's the answer. So when you operate the MOSFET or when you operate the power BJT beyond that maximum voltage, the device suffers from thermal breakdown, thermal runaway problem. All right. So we normally operate the MOSFET within this region. Obviously, the gate source voltage values are essential. Now, the first value is going to be VGS threshold. Below that, the MOSFET is going to be under cutoff mode. Therefore, I will name this as VGS threshold. VGS threshold is VGS TH. And as I was mentioning, this is cutoff. I generally write capital OFF, but people write it as O small ff, not an issue. So this entire region is going to be cutoff, which means applied gate voltage is less than the threshold value. No channel, no inversion layer is going to be formed. No drain current, MOSFET will be turned off. That is the meaning for cutoff region. And the maximum value of VGS, which is plotted on top, I am referring to this point, this curve. So this is going to be the maximum value of VGS, maximum gate source voltage that can be applied. I will write it as VGS max. Beyond that, gate source layer will get punctured. You can't exceed that value. And in between, you now have the control. So the family of curves, they are going to look like this. VGS1, VGS2, VGS3, etc. So on and so forth. I'm not drawing many. There can be infinite number of curves. I'm not drawing them all. Or I'll try to anyway. I'll try to find this. So it must be a flat curve, something like this. Okay, no snakes in between. So when you draw in paper or on a board, due to friction, the line will be straight. Whereas here it's somewhat up and down. And in a transistor, this was not the case. If you can recollect, this curve was not flat. The horizontal line that I am drawing, the ID value remains constant here. That is the meaning. For a particular value of VGS, ID value is going to be constant in a power MOSFET. Whereas in a power BJT, it was not constant. It was keeping on rising. Okay. Reason being, there you have current gain. I'm comparing power MOSFET with the power BJT. Power BJT is a current controlled device. Base current is the control terminal. So current gain beta is given by IC by IB. Output current IC divided by control current base, IB. So it was slightly increasing. Therefore, the collector current was not perfectly constant in a power BJT. Whereas in a power MOSFET, it will be constant because once the channel gets established, beyond that, even when you increase the value of gate source voltage, that doesn't contribute to your drain current. If you want more drain current, you need to go to next setting of VGS. Okay, so VDS value is going to be pretty much constant. And drain current depends on VGS value. So that is the meaning of this curve. And there is one more region that you need to understand. That is cutoff I have marked. And then the important region which demarcates the turn on and turn off is this point. We called that region as saturation in case of power BJT, whereas here it is ohmic region. Saturation region, it is turned on, means ohmic region. MOSFET is entering into ohmic region. The other region is going to be active region. So power MOSFET should be operated between ohmic region and cutoff region. Saturation is equal to ohmic region here. Active region must be avoided. So this is the VI characteristics of the power MOSFET. There is one more curve which is called as the transfer curve, transfer characteristics. I was mentioning the relation between ID versus VGS. So when you plot ID versus VGS, it will look like a straight line in the ohmic region especially. It will be perfectly linear. ID versus VGS. For a particular value of VDS, drain source voltage. So it is going to be like this. And thereafter, it will be a perfect line, perfect straight line rather. Okay, so this is going to be the linear sort of a curve. Linear, I shouldn't write linear region, linear behavior. I will write linear behavior in ohmic region. Now, which is ohmic region? This one. So, in this ohmic region, for a particular value of VDS, you draw a vertical line like this. For a particular value of VDS, you transfer the value of ID, etc. For various value of VGS. You will get a perfect straight line like this. Okay, I'll try to extrapolate that. Of course, you should have done an experiment in your devices. I do not know whether you had all those experiments. I'll deliberately use light colored so that they don't interfere with the other things. This is just an additional information on how you obtain the transfer characteristics. Kindly bear with me. I'm using a very what is this, turquoise blue, very light color. So this is the way you obtain the transfer characteristics. Let's say this is the fixed value of VDS. To obtain your transfer characteristics, you have to have VGS. This is for your understanding. I'm drawing it like this. Don't think VGS is negative. That is not the meaning. Because if I draw like this, you can easily plot the value of ID. This is ID1. This will be ID2. For various value of VGS is again less. Again ID3 is less. So when you join these three dots, you will get a straight line. Okay. This is how you get transfer characteristics. And that transfer characteristics is what I have drawn here. This is the transfer curve. Okay, so for a fixed value of VDS, the plot of VGS versus ID, that is going to give you the transfer characteristics, and it is going to be linear in the ohmic region. This is how we tell that gate source voltage has got a control over the drain current. Okay, these are the VI characteristics of the power MOSFET 1110. Okay. Next is switching characteristics. Quite obviously, the turn on and turn off mechanisms play a role in deciding the switching characteristics. Firstly, we will discuss the turn on characteristics. Now, before we take up the camera is shaking. Yeah. Before we take up the turn on or turn off characteristics, we need to model the MOSFET so that it is easier for us to understand. Again, when you take a MOSFET, it is quite easy to model because you don't have any minority carrier, you don't have any excess minority charge carriers. Therefore, modeling the layers is going to be quite simple. And if you look into the structure as well, there are going to be only capacitances, okay, stray capacitances. Hence, the MOSFET is modeled using as capacitors, quite obviously. Now, the structure or the symbol of a MOSFET, I'll draw the model of a MOSFET here. Before that, the point is capacitances. I should write stray capacitances. Stray capacitances are used to model. To obtain the model of a MOSFET. I'll put MOSFET model. Total the MOSFET bulb. Or used to model the MOSFET. That's all. Now, where are those capacitances and how do they affect the MOSFET behavior? Firstly, there will be the let's take the gate. This is the gate terminal G, and let's take that there is a drain terminal here, drain D, and let's assume that there is a source terminal here. These are the three terminals of a MOSFET. So between gate to drain, you will have a capacitance which is named as CGD, gate drain capacitance. Right? Between gate and source, you will have another capacitance which is named as CGS. We will call this as CGS. And for convenience, I'll draw this below. So this is the source terminal. These are the two main capacitances. Now, when the device turns on in the ohmic region, I'll scroll up and show the ohmic region. So, in this ohmic region, capacitance effect is going to be negligible because the MOSFET is completely turned on, which means capacitance that is completely charged, no change in voltage across that. So there will only be the drain source drop, VDS on state voltage drop. Only that will be present across the MOSFET in the ohmic region. Now that depends on VDS on is given by total drain current ID multiplied by RDS on. RDS on would mean resistance of the drain source layer. Previous session I had mentioned that the drain source ohmic resistance will be slightly more than the power BJT, and I remember to have noted down 3 MOSFET devices whose on-state resistances were 5 milliohm, 6 milliohm, 10 milliohm, etc. So that resistance multiplied by drain current will give the on-state voltage drop. Only that is going to be present across the drain and source during turn on. Hence, once the MOSFET enters the ohmic region, this can simply be modeled as a resistance RDS on with the current being denoted as ID. That's all. This is ID. And then the resistance is going to be RDS on. That's all. This is the model of a MOSFET. Okay. Now, using this, we can easily find out the switching characteristics. We can easily understand the switching mechanism. How does it happen? See, let's take. How do we do that rather? Let's take the turn on characteristics, turn on mechanism. Now, the first thing that happens is the gate source capacitance must be charged. So, for this to happen, there will be some time delay. I will indicate that time delay as TD on. Turn on delay time. TD on refers to turn on delay time. Okay. Second thing that happens is gate source capacitance is now charged. Now the next thing that should happen is remember the VI characteristics. I will scroll up. See, when the gate source capacitance is fully charged and when the voltage across the gate source is more than the threshold. Now for the voltage to rise till threshold, TD on happens. After the gate source voltage has reached VGS threshold, now the MOSFET begins to conduct, which means drain current ID begins to flow only after VGS threshold. Right? Therefore, the drain current will increase. Next thing is ID rises. Now, for this ID to rise, there will be a rise time during which current rises. That's all. TRI. You can name TRI or understand TRI as current rise time. But when current rises, voltage, drain source voltage will not fall. When current rises, the MOSFET is going to be moving from cutoff to active. That's all. At the end of TRI, MOSFET will be in cutoff. At the end of, I will write that as well. Second step. At the end of TRI, rise time interval, MOSFET will be in cutoff. Correction, will be in active region. So the MOSFET was in cutoff here. MOSFET was in cutoff. Then we had charged the gate source capacitance. Voltage was pushed from 0 to VGS threshold. Then current starts rising. Now the MOSFET has moved from cutoff to active. Now the MOSFET is remaining or staying in the active region. All right. Thirdly, now when the current rises, only after the current rises, the voltage, drain source voltage starts falling. So there will be two fall intervals for voltage. Two fall intervals with respect to VDS. They are indicated as TFV1, voltage fall interval 1, voltage fall interval 2, which means the time taken by the MOSFET to move from cutoff till active, stay there, and from active to ohmic region, two fall intervals for voltage. That's all. Once those two fall intervals are over, voltage across the MOSFET would have entered into ohmic region completely. Voltage across the MOSFET will be same as VDS on, and current through the MOSFET would be equal to ID, drain current ID. Now these are the four intervals. TFV1 and TFV2, we can consider them to be two intervals. So delay time 1, current rise time 2, voltage fall interval 1, 3, voltage fall interval 2, number 4. These are the four time intervals. So how do we represent these four time intervals? Pretty simple. I'll try to draw this. Now all these things are drawn considering the gate source voltage as a step function. Let me mark the gate source voltage. Now, as I said, I have considered the gate source voltage as a step function, which means it starts at 0 time and then increases as a step function. Okay, so I have considered a step VGS. Now for this VGS, and that is how we apply a pulse. See, in MATLAB we have applied a pulse. If you try to look at the pulse waveform, it is going to be rectangular or it is going to be a step function. You won't have ramp function, you won't have any sinusoidal, etc. Gate pulse will always be a pulse. Rectangular function, which means a stepped variation, step function. That's all. So nothing technically we are correct only. This is VGS. Next, I need to plot VDS and ID. I will plot both in the same axis. Only then we can correlate. Okay, I'll take one more line for writing something. I need to mark the time intervals, so I'll draw it here. Now comes the time intervals. So firstly, I said on TD on delay time, during which the drain current, nothing is going to happen, only till VGS, after VGS threshold something happens. So if I plot ID is going to be 0. Blue color waveform is ID, and I will use a contrasting color for VDS. which will be probably a darker pink, VDS. So till this time is TD on. This is 0, of course. TD on time, delay time during turn on. I am referring to this turn on delay time. Okay, probably I should use a turn on delay time. That is this first time interval. Okay, fair enough. How will be VDS? VDS will simply be a straight line. Nothing happens to VDS. No change at all. Okay. Next comes, so till TD on, VGS has increased from 0 value till to VGS threshold. We had written the points over there. After this, current starts rising. The drain current will start increasing. So drain current, I think I used this. Drain current starts rising during the rise time interval. Now drain current has, sorry, no worms here. It should be a straight line as far as possible, better. There won't be worms. Worms are there because I am using this laptop screen which doesn't have friction. So when you use a blackboard or a paper, it should be fine. Okay, so this is ID. And this time interval is current rise time, T or I, current rise time, during which current rises, ID rises, but voltage stays there. Drain source voltage, no change happens. Now this is going to be the steady state value of ID. Steady state value, remember I am using capital letter ID, drain current. After this, the MOSFET is fully on. It will keep carrying the entire current ID. No change with regards to the drain current. However, you should understand that good, okay, managed without erasing. Fine. Now, but you should understand that only after the drain source voltage falls to the steady state value, VDS on, MOSFET will be completely on. Therefore, you have two fall intervals, TFV1, voltage fall interval 1, during which the MOSFET moves from cutoff to active. Second time interval, TFV2, during which the MOSFET moves from active to ohmic region. That's all. So those two regions correspond to the fall in voltages, fall in voltage of the MOSFET, which is the drain source voltage. Again, remember, from cutoff to active region, the fall will be steeper. We had come across these things in power BJT also. It will be steeper. From active to ohmic region, it will be flatter. Okay, so you have to draw it that way. So from, let's say, steady state value of VDS must be reached. So it just falls drastically. Okay, so this corresponds to one fall interval. TF, this is this time interval is TFV1, first fall interval. During the second fall interval, it falls gradually like this. Right? It will be even more gradual. Of course, there is a curve here. You won't have this curve. It will be even more. Yes. It will be a sharp, steep fall, followed by a gradual fall in voltage. And once the process is complete, the voltage across the MOSFET, let's take this point. So this time interval will be the second voltage fall interval. After this, there will be the steady state voltage drop across the MOSFET, which is VDS on. That's all. So the total time interval, turn on time interval, is given by, I will write that as T on. T on equal to, you need to add all these time intervals, TD on, delay time on, not capital D here, small d. TD. Okay, so TD on plus TRI plus TFV1 plus TFV2. But generally they take these two terms. That is going to be the on time, because VF1 and VF2, I mean FV1 and FV2, they don't contribute to a large magnitude. So this is the turn on mechanism. I will tell you, turn off mechanism is exactly the inverse sequence of events. I will note that down as well. But remember one important thing. Let me see how many of you are able to recollect and tell me. Now, okay. Now, what will happen to power dissipation across the MOSFET during this portion? During this time interval, not portion, time interval. Okay. Now, especially during this crossover, what do I mean by crossover? Current, drain current rising and drain source voltage falling. Have you come across this somewhere during this session only? I mean, during this course one, in my power electronics course. Voltage falling down, current rising, and there is a crossover, crisscross. Have you come across that somewhere? Therefore, what is happening in the hatched portion, in the crossover portion, power dissipation occurs. Correct? So this is referred to as, when you compute the power that is dissipated during this voltage into current, you can easily compute. That is going to be the turn on area under the curve is going to be turn on power loss. Because the rest of the portion you don't have anything. See, during TD on ID is 0, no power loss. After from TRI till this TFV2, you have power dissipation. So this contributes to power, even this region also. This contributes to power, I mean turn on power loss. See, turn on power loss must be as minimum as possible, which means you need to have a MOSFET which rises fast, whose voltage falls drastically. Only then the time duration that is available, that is going to be minimized. Okay, so turn on power loss must be minimal, turn off power loss also must be minimal. Have this in mind. In general, switching loss must be minimized. That's all. Okay. Now, turn off mechanism, I'll note that point. With that, I'll stop. Turn off mechanism is exactly the inverse sequence of events. That happened during turn on. Sequence of events that occurred during turn on. Occurred question mark. I think one more hour. I am having a meeting, therefore I am in a hurry. Fine. Okay. So this completes MOSFET.